Thank you. So today I want to tell you something about some polynomial Matroid optimization problems, and first the outline. So I will start with some motivation. Why do we consider such problems? After this, a short reminder of Matroids and Matroids polytopes. I think you all know, but some short reminder. We will consider two different optimization problems. The first one with some set of nested monomials, and the second one with monomials fulfilling certain up and downward completeness properties. Indeed, this will give us a hierarchy for solving arbitrary problems, and at the end, some suggestions for future work. But first, the motivation. So we consider polynomial optimization problems, combinatorial ones, and here we will focus on Matroid polytopes. And so I think in the morning we have seen lots of solution approaches, and the standard way is linearisation. So we have some nonlinear monomial, and we do not really know what to do with this. Okay, linearize. There are several ways to do so, or we could, instead of solving it exactly, we could try to approximate via some hierarchies. And especially for some combinatorial optimization problems, there are lots of solution approaches that are really problem-specific, say for the quadratic assignment problem, the quadratic spanning tree problem, or quadratic traveling salesman problem. So, but the problem of linearization is, so the relaxations are often rather weak. So, okay, we can introduce new variables, but something is missing. And we started with trying to better understand what happens in linearizations, what is missing. And Buchheim and Klein suggested maybe start with some polytime solvable problem that it's well understood and add one quadratic monomial. So the advantage of this is that the problem is still tractable, and then we can try to understand this polytope. And if we get some strengthened inequalities, maybe here some strengthened subtree inequalities, we can also then use this if we have a problem with all quadratic terms and just strengthening for each of these single quadratic monomials. So, and that's the aim. We want to consider such problems, but in this talk we want to generalize the results of Buchheim and Klein. We now go to Matroid optimization problems and to sets of nonlinear monomials, and not just one quadratic. Okay, but first, a short reminder of Matroids. So I think you all know Matroids. We have an independent system and this nice exchange property. We will need the following terms. So we will need the rank. So the rank of a set is just the largest size of an independent subset. Then we will need the closure, just add all elements such that the rank is not increased. And then we need separability or non-separability, and a set T is separable if we can find a partition into non-empty sets such that the ranks add up, like this. Okay, so these are Matroids and the Matroid polytopes. As usual in combinatorial optimization, we just consider the convex hull over all incidence vectors of independent sets. And we can nicely optimize over this polytope, so we all know that we can use the greedy algorithm for optimizing. The polytope is well understood, and Edmonds proved that we can do the following. So we just get our polytope if we have the non-negativity constraints and the so-called rank inequality. And we even know a bit more, so we really have a nice characterization of our facet structure. So indeed, we just need the closed sets, and we only need the non-separable sets T. And we will see how this extends then to our nonlinear setting. Okay, so the first problem with some nested monomials. So we are given our Matroid M. So that's just to make life a bit easier. So all single elements should be independent. And then we have this special set E bar. And these are the variables that will be contained in some nonlinear monomial. And then we have an index set, capital K. And we will see in a few seconds what this means. So in contrast to just looking at linear problems, we now look at these optimization problems. So we have here the linear part, and here these nested monomials. Nested in the following sense. So for this index set, we would have a quadratic monomial, then the monomial of the first 5 elements, a monomial of the first 6 elements, and then a monomial of the first 8 elements of our E-bar. So, and now what we want to do is we want later then to linearize and study this polytope. But the first question is, so we did not say something about the size of E-bar. The problem is easy. So we can nicely solve this optimization problem in polytime, and so it fits to the setting that we have some nice problem that we understand well. We have some polytope that we understand well, and so now we try to linearize and understand this more complicated polytope well. So for this, what means linearization? That means we just introduce new variables for all of our monomials, get now these incidence factors, and we study now the larger polytope. And as I said, we want to consider, first, is there a nice formulation for the problem? And of course, then this should be the complete description of our polytope. We want to characterize the facets in the style of the results by Edmonds. And we hopefully want to find some nice separators. Okay, our problem is easy, so we can find separators, but maybe a bit more direct. The problem itself is easy. So you can just check. So yeah, you can do it by Matroid intersection of 2 Matroids, or just check for all. So you can check for k+1 special Matroid optimization problem. So yeah. Yeah. So there are 2 ways that you can solve L+1 Matroid intersection problems or K+1 Matroid problems. So what do you like more? So, okay. But before I can show you the formulation, I need the beta. And the beta are in some sense a bit strange object. So we look what happens if we add an element EI. So if EI is already contained in these sets, nothing happens. We have a 0 in all cases. And then we compare the old rank with the new rank. So we check if there's a new element. So the rank can be increased by 1. And then we check if it's really increased by 1. Then what happens if we do not get a 0 here? If we get a 1 there, then there is some dependency. And later we want to forbid these dependencies in our in our constraints. So maybe some example. So these sets are all closed, so beta 1 is always 0. But just looking at E1, E2, nothing happens. So this is our set T. But if we now have E2 and E3, there's this cycle, there's this new dependency, and we just count a 1. And if we now add E4, then we see some new dependencies, again some 1. And it really doesn't matter if some elements of our set E bar belong to T, then we just have to check the same formula, like here. So again, here's some new dependency with E2 and E3. So, and maybe you can also sum up all the first things. So we just add J elements and compare the old rank with the new rank. So this gives the ILP formulation. Don't look at this, because the red part here, this is just linearization. So we have this nested monomials, and we have, we need some constraints for just building the linear part just without constraints. And then something nice happens. So this is linearization. So if we would cancel this out, we just get our rank inequalities. But now we also add these. So I have not said this, but the betas are always non-negative. And so usually if some of these betas are really positive, we strengthen our rank inequalities. So we will have a closer look at these inequalities on the next slide. So of course the aim is to show that we do not really need the inequality conditions here. So the first thing we have to show in principle would be that they are valid. One can check. Then one would expect this. We can restrict to closed sets because all others are implied by the closed ones. And some picture. So again, this would be our set T. We would have our edges. And now if we would have one large monomial of these 4 variables, we would get a coefficient 1 here. But also in the case if we start with one monomial of degree 3 or one of degree 3 and 4, we would get this one variable here because we just have one dependency. Maybe also to show you that the coefficients do not have to be zeros or ones, they can be larger. It just depends on the degree of the monomial. And in this case, so we have here 2 sets. I just want to remind you that's not closed, that's a separable set, sorry. So we have these 3 monomials, and if you look at this inequality, yes, this is true. So if all these 3 edges are present, then F1 and F2 are both forbidden. So it's possible to have a coefficient of 1 here. And if we have 2 monomials, y2 and y3, then in some sense here the coefficients add up, and we will see that this always happens. So the first nice thing of these rank inequalities is we can separate them in polytime, but here more directly via submodular function minimization. So we just assume that we have some arbitrary Matroid, so this is the best thing we can hope for. And then the formulation I showed you, canceling out the inequality conditions, we really get a complete description of our polytope. So that's nice. And maybe some picture that was a bit surprising for me. We can nicely go from one polytope to the next polytope. So let's consider these 2 nested monomials. So that's the first problem, and that's the second problem. And here just the monomial of degree 6 is missing. And then the only thing you have to do for going from one to the other monomial problem is just adapt the linearisation. Okay, we always have to do. But then we would have the coefficients in the rank inequalities beta 6 with y6, and these ones we just add up. So okay, something is missing, then where does beta 6 go? It just is added up to y8. So it's easy to see that this gives us valid inequalities, but it's maybe a bit surprising that just adapting the linearisation that we really get a complete description in this case then. So, okay. I reminded you that we need closeness and non-separability for facet-defining inequalities of our Matroid polytope. We need something similar here too. So we need an E bar k non-separability. What does this mean? So we have again this partition, but now we also want that the betas add up. Not just the ranks, but also the beta. And this example now shows you that something strange can happen. So we have the same set T, F1 and F2, and now just depending on how the elements of E bar lie in comparison to T, here we have a separable set, and here it's non-separable. So here we would really get some new facet, and here we can, it's not a facet. Okay. So unfortunately here that's not enough. We just say we want closeness and our E bar k non-separability. The reason for this is, but now we restrict to the one monomial case, we need a bit more. So we have these conditions. It's not so important what's really written there, but these conditions ensure that our rank inequalities in the strengthened version are not implied by the linearization. So, and therefore you need this. Okay, but if you have this, then in our one monomial case, you really have a complete characterization of your facet structure. So just extending the results from the Matroid case to a Matroid plus one additional monomial. Okay, that was the first problem. So of course, one says, yeah, nested monomials and then just one chain, maybe not so interesting. So we try to generalize. And the first idea one would have is, okay, let's check with these three quadratic monomials. And one can check, and I also have some, yeah, I think I have the complete description, but I could not prove. So Frank said, oh, maybe just add the cubic one. And then everything is fine. So, of course, no real surprise, but we then generalized this. So we look now again at our E bar and now consider all nonlinear monomials that we can build. So blowing up, really, our problem. And now, why do we call this upwards and downwards completeness? So there was this paper by Buchheim and Rinaldi, and they considered unrestricted 0-1 problems that should fulfill this upward and downward completeness properties. And that's the same, so if you have some monomial, and in the one case, you want to have all larger monomials, or if you have one monomial, then for all subsets of your index set should be contained. And in this case, they provided a complete description. So we know how the linearization should look like. So now we consider this problem. We have our ZE bar, and here are all these nonlinear monomials. Indeed, it's not really the upward-downward completeness of Buchheim-Rinaldi. So we still have some, or we might have some monomials that are still, or where we only have the linear terms. So just for having our Matroid, it's no real sense to do this in the unrestricted case, but here we need them. Okay, and if case fixed, everything is fine, we can solve, we can just check all these cases. So our aim is now linearize again and try to find a complete description and some nice inequalities with some separators. Again, our beta. So we generalize our beta now to set I. So how many elements are added? And we compare the old rank with the new rank. So again, we count our dependencies. But that's not enough. Now we have these, we have lots of monomials, and for our coefficients and our rank inequalities, so if we have a large monomial, say, of degree 5, then it will, maybe some dependency are already counted for a smaller monomial. And so we need this inclusion-exclusion formula. So which dependencies have been counted before and then subtract and everything. So just inclusion-exclusion. So, but with our alphas, we are now ready for giving you the formulation. So the upper part, that's just linearization, so not so important. And here again, just extended rank inequalities. So if we would cancel this out, we have our original ones, and now with these strengthened variants, with these alphas. And of course, the aim is now to show that we can cancel this out. So, and the proof is in two main steps, and some of you, I think you have the proof in the lectures for this, for the Matroids. And we do this in two steps. And the first one is the first one is the complicated step. So if we have, or we assume that we have a facet-defining inequality of our polytope, and this should not be a positive multiple of our linearization constraints, then we first prove, and that's the same like in the Matroid case, that all the coefficients of our linear terms are non-negative. Then we show the same for the quadratic terms. And then, yeah, we show that certain sums are non-negative. So our coefficients might be negative, but summing up certain stuff, then we remain non-negative. And that's really important. So that's the hard part. But if you have this, if you know what happens with these sums, then it's rather easy to show that this is really a complete description. Okay. So again, the nice thing, the separation problem for these extended rank inequalities is again a submodular function minimization problem. And if we still say that k is fixed, some fixed constant, we can again solve in polytime. So, but if we can solve everything in polytime, this induces some hierarchy. So in producing stronger and stronger relaxation, but also blowing up the problem in each step. So in the nice, or in the easiest case, we start with from quadratic monomial. We could also, with quadratic monomials, we could also start with arbitrary monomials with some fixed maximal degree. And the first thing we do is we just determine E bar, so which variables are contained in some nonlinear monomial. And then we use the complete descriptions for all the subsets. So starting with the size 2. So first we would have all quadratic monomials, solve our problem, so adding the linearization, solve our problem, and then check for each of the quadratic monomials if some of the inequalities are violated. So we can determine these, and then in each step enlarge the size. So then all monomials of degree c, 3, 4, 5, and everything, and so on. So of course, this gives us some hierarchy because after E bar steps we are done. No one would do this, but one could. Okay, so we have a hierarchy. One thing I want to note is that we only introduce nonlinear monomials for variables that were originally included in some nonlinear monomial. So we had this linear part, and we do not need monomials with that interact with this linear part. So that's maybe nice. Okay, so finally, some ongoing and future work. So the first question one might ask is, do we really need downward and upward completeness? So if I start not with a quadratic problem, but maybe with a cubic one, do we really need the quadratic terms? And here I have to admit, yes, no. It depends. So if your monomials are, for example, the basis of a circuit, everything is fine. So you can do similar approaches and everything works well. Then in the easiest case you can think of, if your E bar has size 4, and that means you have all the cubic monomials and just one monomial of degree 4. You can prove that this works, but it really needs some time to prove it. But if you enlarge this to E bar equals to 5, and then something strange happens. And what means strange? So I have highlighted this term here. So we consider a graph on a K8, and we get this as a facet-defining inequality. And so we have here a triangle, and add some of, so now we have x variables of our linearized variables. So, and why do I highlight this? Because it does not really fit to the other stuff. So in these cases here, we really get the coefficients like we are used to with these, we count dependencies. But here the problem is it's the smallest monomial that occurs, but this would have a value, a coefficient of 0 if we just consider what happens yeah, with canceling out everything. So in our setting with these calculations here, we would have a 0. And to have a 1 here, yeah, that's not nice. Not for my setting. Okay. So maybe you could ask, can we try with other structures? What's possible if you have monomials that are in pairwise conflict? I do not get complete descriptions for these problems, even in very simple cases, but you get at least strong inequalities. So you can then add up all these coefficients. So you get your coefficient for each of the monomials. You can also separate these, so one can show this. But usually you do not get a complete description. And then it would be nice to get this for the intersection of two matroids. But this might be rather complicated. And here I show you an example why. So look at this small branching problem. So with 4 edges. And then this inequality defines a facet. And that's not nice. So there are 2 reasons for this. First, we have here a negative coefficient. Also, this is the only monomial that occurs. But maybe this, yeah, well, maybe one can handle this. But then we have a 2 here. And in all stuff I've shown you, we just had rank inequalities. We had coefficients of 1. Now we have a 2. And so the situation is much more complicated. We also checked the bipartite matching. There we do not have coefficients 2, but also such negative stuff. And we're not able to prove that we really have a complete description. Okay. And of course, what we could do is we test it algorithmically, our hierarchy. So that's it. Thank you for your attention.